So Ratnesh, can you start now? Yeah, it is already 2:36. Yeah, yeah. Okay. Okay, maybe I can share my screen. For our students, I think they can. Oh, so is it displayed now? Can you see my screen? Yeah, not shared. Okay. So you are not able to see my screen? Hmm. No, but it should be. I don't know. It should on. You cannot see, right? Huh? Hmm? What this? What is happening? Do you have the sharing options? Yeah, because it is not showing me. Yeah, yeah. Now you can see. Yeah, yeah. Okay. Okay. So good afternoon to all of you, and welcome to this lecture. Already, Professor Eric has discussed uh, few of some introduction about neural network, and he briefly mentioned about different paradigms of neural network like recurrent neural network, transformers, uh, and also I think in the subsequent lectures he will be talking about some of the potential application areas of these techniques. I will just introduce you. Maybe many of you who have been knowing AI has been working on neural network deep learning. Probably you know this particular concept. So what I will do is that I will one of the basic concept of neural network is the perceptron. So I will briefly introduce about perceptron. Can you hear me? Hello? Yeah, so I'll be talking about the perceptron and also I'll show you about the steps of backpropagation, how the backpropagation actually happens in the feed-forward neural network. Now, to begin with, there are two broad paradigms of AI that probably you got an idea. One is that symbolic AI, the other one is the connectionist AI. Now, there are lectures on neurosymbolic AI that Professor Eric will also cover, where he'll talk about the combinations of these both approaches, like connectionist AI as well as symbolic AI. But symbolic AI, you can visualize that this is the very classical way of doing AI research, like everything will have to be represented as a symbol. And then there will be a relation between these symbols. And finally, you will have a kind of inference engine. That inference engine will actually help you to do the reasoning process. It has a lot of similarity with what, if you have a computer science background, you might have seen study Turing machines, finite state automata, where everything is represented as a symbol in terms of the string, and then we decide whether a given string belongs to a particular language or not. So you can have a kind of analogical relationship with what symbolic AI does and what the Turing machine-based computation actually is being implemented. The other way that if you see deep learning, neural network, the modern AI particularly, the modern AI is mostly based on the neural network and mainly the machine learning neural network and also these days the deep learning. And the main difference with these two methods, the connectionist AI, you can consider like a human brain where all the neurons, let's say in the brain are connected to each other. And also as a human, we can actually do a lot of parallel processing, distributed processing, right? So for example, sitting in the class, listening to this lecture, probably you are also maybe you are thinking about some other thing that is outside the class. That either very consciously as a human we do, or in our subconscious mind, we always keep on doing that. So that is how inherently our human brain works in a parallel way in a distributed fashions. Okay. Now, can you mimic that kind of behavior into a computer, right? That is what about what the connectionist AI is doing. Now, as I mentioned that in symbolic AI, which is the very classical way of doing the AI, there are different representation possible. You can find an analogy with Turing machine, the von Neumann machine, the lambda calculus, etc. And in Turing machine, what actually is being done that, as I mentioned, that everything is represented as a string. For example, here you can see there is a, we call them as a input output tape. So you can present your input over here. Then there is a scanner, which is your this read write head. The head will point to a particular symbol. For example, currently it is pointing to the symbol C, and then it will make a movement. Now the movement may happen either in the right directions or in the left directions. Okay. So that means what happens is that after reading C, it will decide that in which direction to move, whether left direction the pointer will move or the read write will move to the right directions. And also that there is a state. Okay, so let's say the state is, if I represent as a Q as a state, then when this transition is happening from uh, in either direction, whether left or right, you also have to take a decision that if you are in state EQ and reading a symbol C, then what kind of, let's say, new state you can move to. Maybe you can move to another state, this, and then maybe you can take a movement to the right hand side. It can also be possible that you are not making any changes to the state. That means you are retaining, you are in the same state, but still you are making a transition either to the left to the right. So this is how in computers that Turing machine actually works. And the Turing machine you can consider is a uh, as a kind of general purpose computers that can do basic operations like addition, multiplication, division, all these operations when the computer does. So you can also do it using the Turing machine. And this is a very powerful concept in theoretical computer science. Now we also have another discipline. If you see that systems in computer science, like how a computer actually works, so you can consider it as a von Neumann machine where there is a central processing unit, there is a memory unit. So if you want to add two numbers, let's say 4 and 5, you want to add. So what it does is that the CPU sends an instructions to the memory. The memory is storing these kind of values. Okay. So it knows that in one of the slots, maybe the value of 4 is stored, another slot, the 5 is stored. Okay. So the CPU sends the instruction, let's say the instruction will be like this, that add, for example, 4 and 5. or the address of these two numbers, and the particular memory location where 4 is stored, or the memory location where 5 is stored, these two numbers will be stored into the memory. So that means you are passing an address of 4, address of 5, and memory is a kind of storage device where 4 and 5 are stored. You are sending an instructions. The instruction is sent to the memory. Memory has the storage, the data. Data is fetched to the CPU. Operation is performed, and this operation, the result is again sent back to the final stored in some place in the memory. Okay. So it can happen. Let's say, for example, if 1000 is the address 4, 1001 was the address of 5. So these two will be retrieved, and maybe 1002 it may store the new result 9. Okay, that is how the memory actually works. Now you see that why this is analogous to what do. If you want to recall anything from your memory, if you are observing something from the environment, like always you have to remember in the AI system these 4 different components, that P is the performance measures, E is the environment, A is the actuators, and S is the sensor. So these are very important for any AI systems. There should be a environment on which your AI agent should operate. There will be the sensors through which you have to capture the information from the external world. Then you have the actuators by which you will do some action. And then there will be a performance metric by which you will evaluate the how good is your model. Okay, how good is the AI system in performing certain actions. Now you see that if you want to recall anything from your human memory, okay, if you are observing anything through your sensors, right, from the external world, you are asked a questions, and when you get a questions, then how actually our cognition works. Then we search in our memory that if you know the answers, if you heard this kind of questions before, right, and you try to generate the answers, if it is known to you, if you have heard this kind of questions already, maybe giving the answer is not difficult. And if you remember it well, so you have to recall that whether you know the answer of this particular question. But if you don't know, let's say exactly the question you have not had that is being asked to you, it is unknown to you, unseen to you, then typically as a human, what we do the reasoning, logical thinking, that okay, look, this is the new thing, new environment, a new question I am getting. Now I know the other related things, I do the logical computation in my brain, and then I'll try to answer that particular unseen questions, right? This is very important. That means recalling from the brain, you can say as if you are stored into the memory some information like 4 and 5, and then you are trying to recall those information. You are doing the logical reasoning as if CPU does the computation. So that is basically your logical reasoning, and then you are answering it, right? So you see that this is how it is similar to how neural network actually works out. Okay. Then so we'll continue this. So for example, now if you see that Swapnas, can you hear me? Hello?
Yes, sir. Yes.
But this is disconnected. Oh, on second. Okay. Can you stop the recording? I think I'm disconnected. Please. Hello? Ratnesh? Oh,
Yes, sir. Yes, we are audible.
no, but my headphone is disconnected. Recording को थोड़ा stop करो ना. Set करने दो. So still it is recording. एक मिनट रुको मेरा वो बंद हो गया suddenly. I don't know. My screen is visible, right? Now? Okay. फिर से करना पड़ेगा. I'm sorry. Yeah, Ratnesh, can you hear me now?
Yes, sir.
Yeah, sorry. My screen is visible now. Now? No. Yeah. Okay, sorry for this interruption. So let's continue this. I hope you have now understood that why this connection is KI is getting more popularity these days, because the traditional way of doing the symbolic AI, if you see the differences, that how a human brain actually behaves and how the Turing machine computation in computer actually works out. So Turing machine obviously is always better for numerical processing. It can do many hard mathematical computations. For that, it is really very good. For the programming language tasks, this is also very good. Yeah. So, Gunjan, can you hear me? No. Hello.
Yes, sir. Sir.
Yes, sir. You are audible, sir.
Okay. So for the programming related tasks, for example, if you want to write a program, then obviously Turing machine is very better choice. Uh, Also, this is location addressable. Why it is? What do you mean by the location addressable? The way I give you the explanation of adding two numbers, 4 and 5, into the memory, 4 has a specific location, 5 has a specific location. And those are known as the address in computer science terms. Those addresses are actually sent, and then we retrieve the information from those memory, and then we add them together. So that is why this is known as the location addressing. Okay, and this is a serial processing. We cannot do a lot of parallel processing. Turing machine, if you want to do that more than one task at the same time,
probably Turing machine will not be able to do. Okay. So, but on the other hand, as a human, if you think that if you are multiplying, if I give you two numbers of, let's say, 30-digit numbers, and then if I ask you to multiply them, probably you may not be able to do it very easily. But a Turing machine can do. But if I ask Turing machine that do the pattern recognition kind of tasks, let's say identifying the color, which is red, which is blue, which is green, for example, identifying or recognizing a particular shape, a particular pattern, a particular object. For these kind of tasks, Turing machine is not suitable. For that, you see that as human, we can do it better, right? Any human, you can recognize the colors, you can identify the objects very easily, which a Turing machine cannot do. Human is more learning oriented because we learn from the examples, from the data. We can also, as a human, we learn from our childhood, from the parents, then from the school, colleges, and from the various sources. As I mentioned, that our human brain is parallel. It can do a lot of distributed processing. And when we actually want to recollect from our brain any information, we actually don't send the address for that, right? So, for example, if I ask you a question that why is 2nd October important in India? Why is 2nd October important in India? So then I really don't send the address of each of these words. That why is an address? What is the address of this? Or let's say 2nd October is important in India because Mahatma Gandhi is father of the nation and his birth anniversary is 2nd of October.
Sir?
Yeah. Yeah.
Sir, I just wanted to let you know that your voice is not coming through clearly.
It is not coming.
No, sir. It's been like that for last 2-3 minutes.
Okay. Hello? Can you hear me? Is it better? Ruthness? Gunjan, can you check?
Now it is better, sir.
But still there are noise.
Yes, sir. It's still there noise, sir.
Noise or low voice, you can see the internet is unstable.
It is like your voice is coming from so far, sir. Probably headphone jack is it is properly inserted or not. I don't know, sir.
No, I am using a wireless. Should not have this is good. Hello?
Yes, sir.
Yeah, still there's a problem, right?
No, now it is good, sir. Better, sir.
Is better?
Yeah, it is better now, sir. Yes, sir.
Yeah, please let me know if you are facing any difficulty. Okay.
Yes, sir.
So now this has been all the difference, and so actually we are human brain is content admissible because we directly retrieve the answers from our memory. We don't send the address. Okay. So you can think of that if you want to achieve these kind of tasks, then we need something which is more powerful than the Turing machines, right? That can actually do quite similar thing that a human actually does. For that, you have to understand a bit about the human brain. I'm not going into details of that, but this is the most complex information processing unit, and there are three layers of human brain like cerebrum, cerebellum, and then there are higher brain also. And there is a Maslow came up with 5-tier of hierarchy. So you can closely see this that in the lower layers, so our human brain actually thinks about the physiological needs. Like for example, as a human also. So if you have, what do you think first? You think first about your, let's say, food, You think about your, let's say, some basic facilities like rest, water, warmth, food, etc. So these are all the fundamental needs that are common for every human being. That our lower level of the human brain is actually takes care of this. Takes care means I'm saying that actually all the lower level of the brain thinks about these things, that the physiological needs. Then once you have these, let's say you have food, you have water, you have some basic, let's say rest, warmth, all these things are met. Then we actually go off the higher level in the brain, which actually thinks about the safety. Like for example, your security, your safety. So this becomes important. But for example, if food is not there, if you are hungry, then you don't worry about security and safety, right? So we think about security, safety when these are actually met. Now, once you have food, water, security, safety, then you see that in this layer, now our human being actually think about the belongingness and love needs. For example, intimate relationship, friendship. So these actually come in the third layer of the human being. Then even if you have these, then actually think more about that. So you need the social prestige, accomplishment. You want to do something where people actually get a lot of, let's say, compliment from the people, right? So that prestige in the society, prestige in the community. So these are all of the esteem needs, and that actually happens in this particular layer. And then finally, so let's say at this layer, if you see that some creative activities, let's say good artist, for example, the singer, the composers, uh, scientists, for example, coming up with a good innovations, a new theory mathematician is coming up with a good hypothesis. So these actually are at the higher level brain tasks. Highest level of the brain takes care of this. Think about this. So we can also see that when a neural network works, the neural network actually works in this layered fashion. Okay, there will be different layers. So when you call about deep neural network, so in deep neural network, we have multiple layers of neural net. We have the lowest layer, lower layer of the neural network actually handle some basic task. Let's say, yeah, voice is breaking.
Hello? Can you hear? Okay, now it's better, think? Huh? Now also you have the yeah. So what I was explaining is that these are the different layers of the human brain, that how it actually works. And from the lower layer, if you see that we have the basic needs like physiological needs, then once these are met, then we think about the security, safety. Then once the security and safety are done, then we think about the friendship, relationship, etc. That is the third layer. Then once these are all met, then we actually think about the social prestige, doing something where people can uh, talk about you, give you the let's say credit, or for your accomplishment you are working at this layer, right? And then you have the highest level of creativity, the innovation, creativity, the good artistic attributes. So these are all happens in the very highest layer of the human brain. So now the way the human brain actually works in these different layers, our neural network also happens in these fashions. Starting from the basic needs, let's say if you have a deep neural network, that means you have multiple layers like this. So always the lower layer of the neural network, if you are processing a natural language text, a sentence, you'll find out that the lower layer of the neural network actually handles the structure of the words, the morphology of the words, right? Then if you go into a deep, the second layer probably talks about the syntax, the parsing, etc. Then if you go a little bit upper, so it talks about it captures the semantic information. Now, if you go a bit upper again, in the lot of layers, if you keep on adding between the input and the output in a deep neural network, you'll find out that it will capture the different level of abstractions. So which is very much similar to what actually a human brain actually does. Now, is that fine now? Hello? Hmm?
Yes, sir. It is fine now, sir.
Okay. So now let's see that with this understanding, you can think that we'll actually talk about this a model, a computing model, which is known as the perceptron, probably you know. And the perceptron you can consider as a basic computing element, okay, where there will be certain inputs. And based on the input, certain function will be computed and you will produce an output. So you can consider it is a kind of black box kind. So input is going and some output is getting produced. And this concept is very similar to how a neuron does the computations in our brain. And this is how the structure of the neuron, you can see there are dendrites, which actually captures the information from the external world. Okay. Then you have a cell body, so a storage basically, right? You can store all the information from the outside. So you are capturing it, storing it here in the cell body. And then you are actually sending all such information at different other places, right? For example, there are different connections. So whatever you have stored here in the cell body, now through actions, you actually pass you do some activities here, some computation here, do some operation on the information that you have captured. And those signals you have to now propagate through these actions. So this is how a neuron in the human brain actually works. So capturing information from the external world, doing some processing in the cell body, and then spreading the informations, okay, or generating some actions, relaying the informations to the different parts of the brain, right? Now, this exactly same behavior we have to inculcate into a computing model, okay, that can be useful for doing the computations. And this is known as the perceptron model. So perceptron model, you see like the cell body, the neuron, it also actually captures these information. There are certain inputs like exon, X2 to Xn. There are all these inputs are accumulated at this point. You are doing some kind of operation. Let's say f is a function, some operations you are doing, and then you are producing some kind of output, right? And this W1 to Wn, so these are the different weights. Weight is important because all the inputs are not equally important. So let's say exon may be very important. So the weight of this input will be higher. If you find that X2 is not very important, then it may not be as high weight as this. If you know that Xn is also very important, then this weight, the value of this weight will be higher. So we can set this weight between 0 and 1. And depending upon the importance of this input, you have to assign this particular weight. Lower the weight, importance is the less. Higher is the weight, the importance will be high. This is very much similar to how also we do in our human brain. When you capture the information, let's say this is your brain, and you are capturing a lot of such information, x1 to xn, you can consider. Everything you don't store, don't equally you give the importance, right? You give importance to the more sensitive information or the information that you feel that will be very beneficial, very useful for you. So you also do some kind of assign some kind of priority to each of these inputs, right? That you are getting, each of the information that you are capturing. These weights are actually very similar to that. Now you also have a kind of threshold to compute that is denoted by theta. So typically this threshold function, we can use it as a kind of step function which takes a shape like this. This is your theta and this is the y-axis. The value of y will be 1 if this wyxi is greater than theta, and in this region this is 0. In this region this is 1, and rest region it is 0. So that means this is 0 if you find that xi is less than equal to theta, right? And what is this wy? Is the weight, xi is the input. And you have done the weighted combination because you have captured all the information that you have. Now let us see that with these basic assumptions, so what actually, when we say that we are doing some computation, what do you mean by this? Let's understand with a simple example, the AND gate. AND gate, the concept is coming. It is a kind of two input gate, right? Like here you can see that in perceptrons. But typically AND gate, if you know the digital design, if you have studied it, so we actually represent in this fashion, right? So there are two input gates. You will be given 4 different binary values. This is 0, 0 combination, 0, 1 combination. It can be 1, 0, it can be 1, 1. And what will be the output? If both the inputs are 1, then only the output will be 1. Otherwise, the output are 0. That is how the Boolean function of AND gate. Now, if you want to represent it in terms of perceptron, then you can consider that as if there are x1, x2, two inputs, w1 and w2, there are two different weights, and you have an output y, and you also have to consider a threshold function theta. Right? That is how the same AND function is represented using the perceptrons. Now we know that through the this is 0. So this 0 means what? So if you want to relate it with respect to this threshold function, we know that it will be 0 when this wyxi is what? From this formula actually, right? This one. It is 0 if wyxi is less than equal to theta. Then only y equal to 0. Now, if you want to relate these things, so then it will be what? So W1 is the weight of the first input. What was the first input? 0. W2 is the weight of the second input. This is 0. And since y equal to 0, so this will be less than equal to theta because of that relation that we had defined. So theta here is greater than equal to 0. For this input also y0, so it will be less than equal to theta. So that means W2 is less than equal to theta. Then for 1, 0 also it is, so it will be again, this will be less than equal to theta. So that means this is W1 is actually less than equal to theta. But for 1, 1, the output is 1. So it will be W1 is the weight, input is the 1, W2 is the second weight, input is the 1. So it will be greater than theta because y equal to 1. So ultimately then what you are getting, W1 plus W2 greater than theta. Now you have 4 different equations. One is this one. This is the second one. This is the third one. And this is the fourth one, right? There are 4 different equations. That inequality now you have to solve. And what are the values you have to compute? You have to know the value as W1, W2, and theta. These three variables you have. You have four different equations. Now solve them, which is a kind of mathematical problem now, and then come up with the values that satisfy all these four different inequalities. So one of the possible values, if you solve, let's say W1, W2, and theta, if you set to 0.5, then you see that all these four different equations are satisfied. So theta is 0.5, which is greater than 0. W2 is less than equal to theta. W2 is what? 0.5. So less than equal to 0.5. This is also 0.5, less than equal to 0.5. And this will be what? The W1, W2 is greater than theta, right? Although this is not greater than theta, in this case, actually, it should be greater than equal to theta. But in this case, you see that theta 0.5 greater than equal to 0. This is 0.5 less than equal to 0.5. And this is 0.5 less than equal to 0.5 true. And W1 is 0.5, W2 is 0.5. So 0.5 plus 0.5 is 1, and this theta is 0.5. So this is also validated. So now you see that if you have the values of W1, W2, and theta to be 0.5, then all these four different equations are satisfied. Okay. So this is very important. Okay. Now, this is how you have to do through the learning. Okay. So now, if it is a var functions, you can see that for the var function, what happens is that it will be x1, x2, and y. So it will be 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. This is what the var function. Now again, you write with respect to these wi xi is less than equal to theta or greater than theta, depending upon the value of y. If you write those four inequalities, you will get values like this: w1, w2 equal to 1 and theta equal to 0.5. Now, if you have an XOR functions, in XOR function, what happens? So these two are 1, but here you will get a 0. That is what this XOR functions. Like, now what will be the four inequalities? The first case is 0, so it will be W1, the first, this is W1, the first weight. This is W2, weight for X2. And since Y is 0, so it will be less than equal to theta. So theta is greater than 0. Then for the second input, it will be W1 into 0, W2 into 1. And the output is 1. So it will be greater than theta. So it will be W2 greater than theta. Then the third one, W1 is greater than theta. This is also 1. But for this one, you see now it is 0. So it will be less than equal to theta. So W1 plus W2 is less than equal to theta. So now can you find out the values of W1, W2, and theta that will satisfy each of these four inequalities? That is not possible, right? There is no such values that actually satisfy these four different equations. So this is the problem, and that actually needs more discussion, how to solve this kind of problems. But I hope you got an idea that how the perceptron actually is computing, right? How the computation is getting done in the perceptron, how the weights are actually being calculated. And here the weights we can consider W1, W2, theta is the threshold. But later on, we'll see that theta will also be considered as a weight that you have to learn from the data, actually, training set, we can say, okay, while you are learning. Now, very quickly, I'll show you that how typically the perceptron training happens. Initially, with respect to the threshold function, this computational law now, the equal to sign, it was basically Wi this case, it was less than equal to theta, if you remember. Now you are ignoring this equality sign. We are ignoring it, and we are strictly considering this is greater than and equal to, greater than and less than. So that means our original representation where we have less than equal to, now we just modify it and we remove this equality sign. We just keep the less than sign here. The second step, what you can do, rather than this theta, theta can also be considered as a weight. How can you consider theta as a weight? So this is very simple. If you just bring this wy xi minus theta, it will be greater than 0 in this case. In the second case, it will be wy xi minus theta. This is less than 0, right? So now this theta you have brought to the left side, and then you can introduce a new input for it. Let's say x0 is the input and w0 is the weight. So what you can consider that w0 x0 equal to minus of theta. That is what we are considering. So in this case, you see that is what is done. So theta is now absorbed as a weight here. So you introduce a new input, which was not an actual input, and set it to value -1. W0 is now theta. So if you do W0 into X0, it becomes minus of theta. And then you negate all the zero class examples. Okay. That is the second, that is the third step. So you have binary classification. You can consider one as the class 1, the other is the class 0. So now in this case, OR perceptron, OR gate, the one class is what? So 1 we can get from 1 1, 1 0, and 0 1. 0 class is only 0 0, right? So now what this augmented x vectors? Augmented x vector is nothing but this theta, the threshold value, the threshold parameters that you are considering also as a weight. So all these vectors now will be augmented because it was minus of theta, minus of w0 x0 basically. So that is minus of theta. So here the value of the input x0, the value of x0 is -1. So if you multiply with -1 into theta, so ultimately it becomes minus of theta. So the value of x0 is -1 here. So you are adding this, augmenting means nothing but this. All these vectors, you are adding this one more dimension, okay, component, that is -1 1 1, -1 1 0, and -1 0 1. Okay. And for the 0 class, we have what? Again, -1 and 0 0. So this is one class example. This is 0 class example. Negate the 0 class. This negation has a meaning because you are actually trying to bring all the vectors in the same direction. So if you just negate these values, so it will be what? It will be 1, and then it is minus of 0 means 0, minus of 0 means 0. So that means you are just changing the direction of this, and you are bringing it in the same direction in which these vectors are. So you do this negation, and after doing these negations, now what will be the vectors? Your original vectors was like this: -1 0 1, -1 1 0, -1 1 1 1 0 0, and the vectors from this you have to do the training. Okay, so training process is also in neural network. If you do the training, one problem that you will find out is how to do the initialization. What do you mean by the initialization? By initialization, we mean nothing but assigning. We have this wi and xi, where xi is the input. These weights you have to assign. Now, initially, these weights can be random. So let's say we have randomly assigned the weight, and all the weights we have set to 0. And then you do the testing. If wi xi is greater than 0 or less than equal to 0. Until and unless for every input, this particular equation is satisfied, you have to continue doing the training. And whenever you get Wixi less than equal to 0, immediately you have to update the weight. This is the weight updation rule. So W next is the next weight, that actually what was the previous weight, plus for which vector this test condition has failed. Okay. So let's see that what we mean by this. Okay. For example, these are x1 and x2, w1 and w2 and y. And if you have a NAND gate is basically 0, 0 to 1, 0, 1 to 1, 1, 0 to 1, and 1, 1 to 0. So why this NAND? The opposite of AND. That is what the NAND. Okay. So if it is 0, 0, in the AND gate, you will get a 0. In the NAND gate, it will be 1. Okay. In the 0, 1, the AND gate is 0. So you are getting a 1. So this is just the reverse of the AND gate. And then you have captured the theta as a weight here. And eventually, following the same way that these three vectors, let's say x0 is an additional vector for theta that you had introduced, which has a value of -1 everywhere. And then you can, this is your 0 class, so you have to negate these particular vectors. If you do the negation, then V3 now appears, as you can see here, that this is -1, and this is +1. Okay. So now this vector, so these are your inputs, basically input vectors: 0, 0, -1, 0, 1, -1, 1, 0, -1, -1, 1, 0. These are all your input vectors. Now you have to start doing the training. So initially at step 0, you see that since you have W2, W1, and W0, these are the three different weights. So you randomly assign all these weights to 0. You don't have to do anything. And then if this is 0, 0, 0 is the weight, you see whether WV is greater than 0 or less than equal to 0. This testing you do. Now WV is greater than 0. How do you do that? So you go back here. This is 0, 0, -1, right? That is V0. So if you do in the first case that W, this one, these weights into V0. So W into V0 is what? This is 0, 0, 0 is W dot V0 is, you can see that 0, 0, -1, right? You just do the element wise multiplication. It will be 0 into 0, 0, 0. This is also 0. So ultimately it becomes 0. So if it is 0, then it becomes less than equal to 0, not greater than 0. So less than equal to 0 means what? If it is 0 or less than that, then you can say that you cannot stop training. So you have to update the weight. So the V0 fails means what? Because for the V0 vector, this W into V0 is not greater than 0. So this is a failure vector. That means this weight that you have assigned, this is not the perfect weight. You have to actually do some kind of updation to this particular weight. And how the updation will happen, like for example, here you can see that the initial value, initial weight, that means the previous weight here, plus the particular vector for which it has failed. So for which vector it has failed, this was the input vector for which this has failed. So we add these two things, and then it becomes 0 plus this 0, element-wise addition. 0 plus this 0, 0 plus -1, so it will be 0, 0, -1. So that becomes your modified weight. Again, you start from the beginning. So what you mean by the start of the beginning? Now W1 into V0, you compute. What is your W1 now? Let's say 0, 0, -1, and V0 is what? 0, 0, 0, right? No, 0, 0, -1. It was -1. V0 was, if you go back, 0, 0, -1, right? So now if you do the multiplication, 0, 0 is fine, 0 plus it can be 0, 0. Let's say this is also 0, but this is -1, -1. So it will be +1 basically. So this is 1, right? If you do the multiplication. So this will be plus basically. So element wise, you do the multiplication and then addition. So it becomes 1 basically, because this -1, -1, this is 1. So that means it is greater than 0. So it is not failing. Then you consider what? Then you consider W1 into V1. So what is W1 into V1? 0, 0, -1 into V1. Again, you go back. V1, you see 0, 1, -1. Right? 0, 1, -1. Okay. Now 0, 1, -1. Again, you do the multiplication element wise and then do the addition. So it will be 0 into 0, 0, 0 into 1, 0, -1 into -1 plus 1. So again 1. So this is also not failing. Then you go to V2. V2 is this 1, 0, -1. This will also not fail, because if you multiply with this -1, it will -1 into -1. Ultimately, you will get a +1. +1 means it is becoming greater than 0. It is not failing. But when you come to this now, V3, right? -1, -1, +1. So now, if you do that W1 into V3 here, so W1 was what? 0, 0, -1. V3 is -1, -1, 1. Now you see that this -1, 1, this is 0, -1, 0, 0 into -1, 0. But -1 into 1, this will be -1, right? And this -1 means less than 0. So it is failing. So V3 vector actually, this weight combination, this particular weight combination is failing for the V3 vectors. Okay. So you have to again update. And how to update that? This value, current value, that is 0, 0, -1, plus the vector that is V3 for which it has failed. Then you do the additions. Okay. So now the weight becomes -1, -1, 0. Now again you do that, okay, what is V0 into W2? What is V1 into W2? What is V2 into W2? What is V3 into W2? So everything again you repeat. And if you do that, you see that very beginning you will fail only. V0 into W2 will be less than 0, because this is -1, -1. You see that here -1, -1, 0. So now if W2 is -1, -1, 0, if this is your vector and this is the current vector, then it will be 0 into -1, 0, 0 into -1, 0. But this -1 into 0 also 0. So you see that W2 into V0, it will be less than 0, less than equal to 0, right? Because it is becoming 0. So here itself it fails. So now you have to update this weight by adding with this. So it will be -1 plus 0, -1, 0, -1, -1, and 0, -1, -1. It will be then what? -1, -1, -1. So this is how these weights are coming here. And keep on doing this from one iteration. You update the weight. You do the element-wise dot product with each and every input vectors. A particular input vector for which it is failing, immediately your algorithm fails, your training will not be successful. So you have to again update the weight, you have to go back, and then again you have to reiterate. And that will continue from one iteration to the other iteration. This weight updation will happen, checking with each and every input vectors will happen. And eventually, if you find that there is a situation where after this iteration, you will encounter a value like -2, -3, minus this 4. And for that, now, if you do this, that W18 into V0, W18 into into V1, W18 into V2, W18 into V3, all will be greater than 0. Everything will be greater than 0. So that means you get an idea now that this is the value, this is the perfect weight combination for which your input training has been completed, because all the input vectors V0, V1, V2 to V3, all the input vectors are getting the success. Now, while you do the perceptron training, and when we talk about perceptron training, we actually want to come up with this very concrete or the set of values, weight values, for which this particular condition will be satisfied. Okay. Now there are theorem for this, that when the perceptron training will convert. So I am not going into details of that, but Marvin Minsky, okay, very well-known AI scientist at MIT, he actually came up with this concept that when a perceptron training actually converges. So whatever may be the initial choice of weights, in our case, we have set it to be 0, 0, 0. You can set to any values, whatever way you want. You can set 0 0.5, 0 0.5, 0 0.4, any combination, whatever may be the initial choice of the weights. And whatever input vectors you are choosing for testing, the perceptron training converges if all the input vectors are from a linearly separable function. This is very important. Okay, so you have to see that. So this is the proof of that. I am not going into details. So, but if you are interested, I can tell you that how actually it does. But this is basically due to Marvin Minsky. Also, if you find that a particular weight is continuously getting repeated while you are training the perceptron, then it gives an idea that your function is not linearly separable. So for example, you are going from one iteration to the other iteration. So whatever was the weights in the earlier iteration, if you see the current iteration also is repeating the same weights, okay, then all the vectors are not linearly separable. This also is the another side of the proof. And this is very trivial and very easier to prove. It is not very difficult, okay. So any questions so far, by the way? So if you have any questions. Any questions on perceptron training? Because this is a very foundational concept.
Sir.
Hmm.
So by doing this exercise, is our target is to find linear separability, or we just want to find any way of separation?
No, the perceptron, you see, the algorithm says what? So if it has to convert, then they should be linearly separable, right? You have to bring them uh, by doing the linearly separable. So you can guarantee that it will be converging. Otherwise, you cannot guarantee. Okay. So if it is linearly separable, that guarantees that convergence will happen. Okay.
Okay.
So let's the XOR gate. So XOR gate is not a by single layer perceptron. You cannot solve it, right? Because an XOR gate, if you draw, right, so you cannot really solve it, because for 0 0 you have 0, 0 0 input you have. Oh, sorry. 0 0 input you have 0, 0 1 you have 1, 1 0 you have 1, and 1 1 you have 0, right? So that way I think this will not work out, because you cannot really draw a single line that will actually help you, right, solve your purpose. Because you see that 0 and 1, so you will plot the values in two-dimensional axis, right? So then if you plot the values that will having for the 0 0 you will get a 0, 0 1 you are getting a 1, 1 0 you are getting a 1, and then if you want to separate them, that separate them means I am saying that drawing a line that separate the examples, the combination for which you have a value of 1, and on the other side you have those combination for which you have a value of 0. So let me see that what I mean. Yeah, so you have 0 0, right? So 0 0 you are getting a 0. So like this. So what is happening? Let's say 0 0 is 0 means what? 0 0 any point, this kind of point, let's say. So then 0 1 maybe this kind of points it is happening. Then 1 0 maybe this, and 1 1 maybe at this point. Now for 1 1 you have the output 0. For 0 0 you have the output 0. And for this you have output 1. For this you have a output 1. This is how it looks like, because this is the 1 1 output 0, 0 0 output 0, 0 1 output is 1, 1 0 is output also 1. Now can you draw a single line and can you divide that these 2 0 will be on one side of the line and 1 1 will be on the other side of the line? Are you getting the point? So for example, these 2 1, so these 2 points will be on one side and these 2 points will be on side. So can you draw a single line to separate them? You cannot do, because let's say if you are doing this, then what happens? There is overlapping, right? One is here, this one is this side, in two different sides. You draw any line, single line. You cannot really discriminate them, right? By any linear single linear line that will discriminate these two different inputs having the 0 value as the output and 1 value as the output. So that becomes a kind of tricky problem, and that actually needs more discussion, more sophisticated algorithms, more refinement. So then you have a feed-forward neural network, and I believe that backpropagation, you know, that which is very fundamentals for any neural network. So any neural network that you do, whether it is a CNN, whether it is a recurrent neural network, whether it is a transformer, whatever kind of neural network you are doing, the error minimizations, the backpropagation is an inherent step, right? So you have to do it. So, so any further questions? So backpropagation probably we can see, so we can discuss it. Any idea? Otherwise, maybe we can move to the other part of today's lecture. So I'll continue again with the. So Ratnesh, are you there? So maybe you both can start now at 4, right? You have to start. Okay. But if you have any questions, you can ask me about AI, not only from this topic, any topic. Let's say AI, NLP, machine learning, if you have any questions. About the course.
So, Professor, my research area is in the field of quantization, like how we can make it more parameter efficient, the language models. So That is something I chose because like that time this particular domain was very hot, like
Okay.
Qlora had come in. So I need your direction on like choosing like which research area do you think will be like the next frontier that as researchers we can think about.
So you are in which year of your PhD now?
So, Professor, I am an industry participant. I am not doing PhD, but right now, like you are expected to publish in the industry also to be considered
Yeah,
a
yeah,
senior.
yeah, yeah, yeah. That's true.
Yeah, so that's why.
Yeah. So quantization you are doing. So do you have any target specific tasks in your mind, or you are uh,
So,
doing at
Professor,
the basic?
can we did it for a conference, so we did it for like a classification task, which because that is the one which is most utilized. However, I am open to like any research problems, not just related to like quantization or LLM. Just need your general like guidance.
Yeah, yeah. No, you see that because of this large language model, okay, vision language model. So these days, particularly, many things you can get it done through the large language model. It's very difficult. Like, for example, Chat GPT, if you see GPT-based model or open source model. So there you'll see that for many of the tasks, this really does well. So now, what happens is that, let's say, reasoning can be one part as a next step, that whether it can do the reasoning properly. And also, if you have multiple LLMs and if you have a kind of a multi-agent framework, right? So agentic framework where you have, and can you do you have to do a proper planning. Let's say one agent is Llama, for example, another agent is DeepSeek, another agent is GPT. Now, if you have these three different kind of agents, now once the task is being given, so it needs a kind of proper planning, right? So how the task is to be transferred from one LLM to the others. So the planning will also be very important tasks, planning the LLMs, then the reasoning part of the LLM is very important. The another thing also, if you see that all over in the world, even in India also, I spoke about India AI mission. There also you have seen that for uh, LLM is good uh, for the high resource scenario. The, let's say English language, the European languages like Spanish, German, French, for example. Now, some of the Indian languages are okay. Asian languages like Chinese, Japanese, Korean, so they are well. But if you think about the other languages where resources are very little, very less. For example, if I ask you about something on Bodo language, Maithili language, so how can you actually build a language model for that? So what I'm saying is that under resource constraint scenario, resource is not only I'm saying the computing resource. Resource is also I'm saying the data resources. Okay. So now under that scenario, can you build a very, let's say, acceptable, very good foundational models, okay, uh, under this kind of scenario where computing power is also is a problem, as well as the data availability is also the good quality data is also a kind of problem. So now can you do for example, language similarity understanding? So if you know for Hindi, you have built a good language models. Now, if I ask you to do it for Punjabi, if I ask you to do it for Marathi, right? You see that Hindi, Marathi, Punjabi, even Bangla also, they all belong to the Indo-Aryan language family. They have some kind of similarity. So while you are building the models, the LLMs for the other languages, whether this kind of linguistic similarity can be leveraged on. Can you leverage the language characteristics between, let's say, similarity between Hindi and Marathi, Hindi and Punjabi, to quickly build the model in Punjabi, if you have the Hindi LLM already. Okay. So these kind of, I think, theoretical insights, okay, so are needed, that language specific characteristics that can be interesting to build the large language model if you want to do it from the very scratch. Okay. So this is how I think the field is progressing.
And
Okay, that
Professor, thanks. Just one follow-up question. These are very fascinating topic, multi-agent reasoning, Indic languages. And Professor, I met someone from your lab and he shared his work that he was working on evaluations. So I wanted to ask, like under reasoning and evaluation, one under reasoning, like what tasks can be done? And second is evaluation is also a good direction according to you.
yeah, evaluation obviously is very good. Yeah, evaluation also, that how to evaluate, you are saying from my lab, whom do you meet, by the way? So Man, you are saying he is currently working with me.
Professor Rachit, I met Rachit at the campus.
Oh, you are in the campus now, huh?
Yeah.
Oh, very good. Sorry. I missed the chance to meet you. But anyway, yeah. So this will be also important. Yeah, that is also important task. Maybe evaluation, but I am saying not the human evaluation only. Let's say, can you get the come up with a method where LLM will be serving as a evaluator, LLM as a judge, for example, right? So this evaluation is not by a human evaluation I'm talking about. It will be more interesting that can you